Lesson 3.1, Derivatives of Polynomials and Exponential Functions, Part 2. This is where we look at the exponential function. An exponential function is a constant raised to a variable power. Let's go ahead and use the definition to find the expression for the derivative. Here's the derivative, definition of derivative, and we use the function a to the x power in the definition. Notice that we can separate these exponentials, and then we can factor out an a to the x, and at this point we can actually take this expression outside the limit because it doesn't have an h in it, and we have the derivative expression. It actually is the original function times this limit, and this limit is quite interesting. Let me rewrite the limit in another way. I could write it as a to the 0 plus h minus a to the 0 all over h. And hopefully you'll recognize that as the derivative at a particular point, which happens to be 0. So one more time, the derivative of an exponential is itself times the derivative at 0. The derivative at 0 of this exponential function. Let's go ahead and use our calculator to examine what's going on. I'm going to put 2 to the x power here, and you can see my derivative expression here, and I'm going to go ahead and hit graph, and there's my 2 to the x power, and here is my derived function. Now I'm going to evaluate by pressing second calc, and I'm going to evaluate 0, and I want to do it for the derivative. Notice that the derivative's value at 0 is 0.6931. So what this function is saying is it's taking every y value and multiplying it by 0.6931. And that's why the derived function is sitting lower underneath the original function. Let's go to y equals, and I'm going to change my base. I'm going to make it 3 to the x power, and I'm going to graph. And here's 3 to the x power, and here's the derived function. I'm again going to evaluate it, the derived function at 0, and I'm going to look for the derived function. Now I want you to notice that the value of the derivative at 0 is 1.09, and with all the rest of those numbers. So I'm taking 3 to the x, and I'm going to multiply it by that 1.098, and you can see that the derived function is sitting on top of 3 to the x because I'm multiplying by a number greater than 1. All right, so let's take a look at this in table form. Remember, the derivative is the exponential times this limit. And we're going to examine the limit with base 2 and the limit with base 3. These are the numbers that we came up with. Getting closer and closer to 0, we're getting closer and closer to these numbers. This begs the question that is there some base, don't know what it is, in which the derivative is equal to 1. Here's a number here's the derivative that's less than 1, here's the derivative that's greater than 1. Is there a base between 2 and 3 that will yield 1? Okay, again, the derivative of 2 to the x is this, 3 to the x is this, and the derivative, these are evaluated at 0. So the derivative is these numbers times the exponential function. So this constant times the value of the function. And the answer is yes, there does exist an a in which the derivative at 0 is equal to 1, and we call this base e. So e is the number such that the limit as h approaches 0 of e to the h minus 1 over h is equal to 1. All right, so here is y equal to 3 to the x power, y equal to 2 to the x power, and here is that base that's going to satisfy that requirement, in which at 1 the slope of this e to the x is going to be equal to 1. All right, so the derivative of e to the x will be equal to itself times the limit as h approaches 0 of e to the h minus 1 over h, and this e has been defined to yield this limit to be equal to 1, and that's what we're getting right here. All right, let's go ahead and graph the functions of f and f prime, but we want to find f prime and f in the second derivative. So f prime of x will be equal to e to the x, which is itself, minus 1, and then the second derivative will be equal to e to the x. Okay, let's compare f and f prime. So here's f, and let's take a look at its derivative. The slope of the tangent line is negative, which is exactly what we're getting, a negative value at that x value. Right here, the slope of the tangent line appears to be 0, which indeed, that's the value of the derivative at that point. Right here, the slope appears to be positive, and the value of the derivative at that point is also positive. All right, let's take a look at what point on the curve y equal to e to the x is the tangent line parallel to y equal to 2x. So we want to compare the slope of this function with the slope of this function. So we're looking for some value a, we know that e to the a, because the derivative of e to the x is itself, but we're looking for that a value, e to the a, where it equals to this slope. And when we use our algebra process, we're going to take the natural log of both sides, and we're going to isolate a, and a will be equal to the natural log of 2. So this is the answer. At the natural log of 2 on the e to the x curve, that slope is equal to the slope of the line. And this is the end of the screencast.